Welcome to Section 1 of Unit 4, Current and Resistance. This unit corresponds to Chapters 19 and 20 of the purple Survey Physics book located in our classroom. We're going to start with some definitions. Our first definition is the definition of electric current. Electric current is rate of charge flow or cross-section of charge flow per second. And current, which is represented with an I, is charge, so Q is charge in coulombs over time in seconds. So the unit for current is a coulomb per second, and we've chosen to use Ampere's name. Ampere was a French physicist. And the unit that we choose for coulombs per second is called an amp in the U.S. Again, the symbol for current is an I. Sometimes that can be a little confusing because people think of C for current, but it's I for current. It's important for us to remember that electrons are moving in the conductor, not the neutrons or the protons. And we'll look at we'll go ahead and take a look at a animation of this. So here is a conductor with resistance, and the big yellow dots represent resistance. And now what I'm doing is I'm turning up the current, and we can see as I turn up the current, there's more electrons flowing, and they're flowing faster. But it's not perfect. You can see here that as I zoom in, that some of the electrons are actually going backwards. Some are going very quickly. They're finding spaces and going through. And others are bouncing off of the lattice structure. So it turns out that current and resistance at the atomic level are actually rather complicated. And what we end up doing is just sort of simplifying it like we do with many things. And in the United States, we have an interesting quirk, which we'll talk about in person. But the interesting quirk is that in the United States, conventional current is described as the flow of positive charge. Now, we know that the positive charges aren't really flowing. But typically what you'll see in the U.S. is a symbol for a battery. Here's a symbol for a battery. I'll label the positive and negative sides. And I'll add in a resistor. So here's a very simple circuit. And in the U.S., we'll say that the current is coming out of the positive. So we model it as positive charge flow. Now, we do this because way back, before we understood exactly what was happening at the atomic level, we had to guess. We had to make a guess, and we guessed wrong, and we kept it that way. The rest of the world would say it's negative charge flowing the other way, which is equivalent to positive charges flowing. Here we've got positive charges flowing counterclockwise. That's equivalent to negative charges flowing clockwise. Again, this can be a little bit confusing for American students because we know that positive charge is not really flowing. But more on that later. When a circuit is completed, an electric field is set up in the conductor, and it travels close to the speed of light. This number here, this 3 times 10 to the 8th, is the speed of light. And so this is part of the reason why we studied electric fields before we began our study of electric current. There are 2 types of current that we're going to look at. We're really going to focus mostly on direct current. Direct current is current moving in only one direction within a conductor. And direct current is the kind of current that's supplied by batteries and the power supplies that we have in the classroom. Alternating current is current that is constantly switching direction within a conductor. This is what household current is in the United States. And in the United States, the current actually flips direction 60 times per second. So if you look at a standard outlet, you'll see one side, if it's a grounded outlet. One side is a bit longer than the other. This kind of looks like a smiley face. But this longer side is the positive terminal, and this shorter side is the negative terminal. But really what happens is these actually flip-flop back and forth, positive and negative. The positive and negative reverse positions 60 times per second, 60 hertz. Hertz, named after a German physicist, 1 hertz is simplified or abbreviated, HZ, and it means 1 cycle per second. So 60 cycles per second, if you can imagine that. And we see the effect of that 60 cycles in things like fluorescent light bulbs, and in there are other things like old cathode ray tube TV screens cycle through at 60 cycles per second. Okay, so we've looked at, in this first page, we've looked at current. And again, current being charge flow. And I told you a lot of extra stuff about current, but the main thing that you need to know is that current is charge per unit time. Let's look at the next component of a circuit, the next main component, and that next main component is resistance. So all substances have resistance to charge flow. This is because the electrons collide with metal atoms as they travel through a conductor. They're slowed down on their journey, and they also lose energy due to the many collisions that they encounter. So that's what we see here in this picture, is we see the resistance. By the way, I should shrink this down a bit. As I turn up the current, we can see that the brightness at the top is going up as I turn up the current. So back to my notes here. There are several factors that affect the resistance of a conductor. One is the length. So a longer wire makes more resistance. Next is cross-sectional area. A fatter or a bigger area is going to create less resistance, so we can see that here. The material affects the resistance. So copper has less resistance than aluminum. Gold is the very best, or one of the very best, and silver. Aluminum has more resistance. In the 60s, they tried to save money by wiring houses with aluminum, but the resistance was high enough that it actually got kind of hot, and that is bad. You do not want a fire. Finally, temperature can change resistance. So here we see, this is a little bit hard to see, but I'll zoom in. This is a higher temperature. And a higher temperature creates more resistance. So putting these four things together, we can see that the resistance of a conductor is equal to its resistivity. This Greek letter rho stands for resistivity. And it is particular to a substance. In other words, each substance has its own resistivity. The length, this should actually be a cursive L, the length of the wire over the cross-sectional area. Typically, we work with resistors at room temperature, although it is good to know, and we'll see this in lab, that if a resistor heats up, its resistance does change, and sometimes it also burns, and we may get to smell that in lab. The types of resistors that we will work with are mass-produced, and they look like, the ones that we have look like little brown cylinders. And on the little brown cylinder, there will be 4 stripes. And the stripes are a different color. So I'm going to draw a sample resistor here in color. And what this does is it tells us the resistance without printing a number. And the advantage is if I were to rotate this resistor around, I could still see all four colors and tell what the resistance is. So the first color that I see here is red, and when I look on this chart, red is a 2. And the next color that I see is brown, and when I look on the chart, brown is a 1. So I know that the resistance is 21 times something. The third stripe is the multiplier. So the multiplier here is just 1. So 21 times 1 tells me that this is a 21 ohm resistor. And then the last stripe is the tolerance. And this is a silver stripe, and it's 10%. Well, 10% of 21 is 2.1. So I know that this resistor is within 2.1 ohms of 21. In other words, it's, let's see if I can do this math in my head, 18.9 to 23.1. I know that this resistor is somewhere in this range. And that's what tolerance means, is that it's expected to be 21, but it will be, or it should be, the company is claiming it will be within this range. Okay, so putting this all together, we have 3 things to look at. The first one, or the one that we haven't talked about yet, is voltage. Voltage is potential difference. And it's what pushes the electrons through the circuit. So I'm going to go back to this animation yet again. So when I look at this animation and I see the electrons flowing, I have to ask myself, why? Why are the electrons flowing? And they are flowing because what's not shown here, let's see if I can make this work. What's not shown here is that there must be some sort of voltage. So if this is my resistor, actually there's kind of a picture of it up here. In order to get those electrons to flow, there must be a battery. It could be a capacitor. So it could be a battery, it could be a power supply. Later in this course, we're going to talk about generators, how you can generate current. It could be a capacitor. But we need something that that makes the electrons want to move. I'd also like to point out, this might be a little bit hard to see, this is the positive side on the left, and this is the negative side on the right. The electrons are moving toward the positive. I'm sorry, the electrons are moving toward the negative. So they would come around like this. Okay. It's helpful to visualize these things, and it will be more helpful as we go on through this unit. So we did a lab with Ohm's Law where we set up a very simple circuit. We measured current with an ammeter, that's what the A is for. We measured voltage with a voltmeter, and then we graphed it. We put voltage on the y-axis and current on the x-axis, and some of us got a straight line and some of us didn't. When we do get a straight line, we call the substance ohmic. The reason we call it ohmic is that if the slope is constant, the resistance is constant, we say that it's ohmic because it has a constant resistance. We also use this as evidence for V equals IR, which is called Ohm's Law, which is the relationship between voltage, current, and resistance. Okay, I'm going to pause and give you a chance to review these notes, and then you can go on to section 2.